Okay, so yesterday we were discussing induced representations. So the situation is G is a finite group, as usual. H is a subgroup of G, and it's useful to discuss things from the point of view of CH, of modules. So suppose that W is a module, a CH module, so it's there is a representation for the subgroup H, and then the induced module, the induced CG module is say conveniently expressed as a tensor product. So the idea, you have W, which is a right CH module, okay, and then you have CG here, which is a bimodule, meaning is the right CG module because you multiply on the right. We can multiply on the right by element of itself, and a left CH module. Okay, you multiply on the left by CH, and then you take this tensor product over CH, meaning that elements of CH can go from the left here to the right here, and this is a CG module, because recall that these two in a sense cancel out. Okay, so if there is no action here, then this is just an abelian group, actually a vector space in this case. But since there is this becomes a CG module. And we had seen, at least in the case when W is irreducible, but then it's true. I don't want to discuss this too much, but then a direct sum argument shows that this is true, always true, that this module, this induced module, is a direct sum as vector spaces, say, of what? Of the module W times, okay, let's write T1, direct sum T2, direct sum until W Tk, where T1 Tk, where K is the index of H in G, and T1 Tk is a so-called transversal for H in G. Meaning that the cosets, that the right cosets of H in G are exactly, they are K by definition, HT1, HT2, HTK. Okay, and I mean I have written T1, but we take the assumption that T1 is 1. I mean one of these cosets has to be H, and suppose it's this, and we choose as representative 1. This is just for simplicity. Okay, so it's a direct sum of vector spaces. We had seen it by comparing, by finding an isomorphism with this, okay, which is inside CG, okay, because this W, if it's irreducible, this W sits inside CH, okay, because each irreducible each irreducible CH module is contained, that we have seen in the group algebra, in this case of the group H. This is of course contained here, and so everything takes place inside CG. Okay, as I said, this works if it's irreducible. Otherwise, there is some argument and you are fine. Okay, now assume we have this, and we want to realize what kind of representation do we have. Okay, what's or better, what's the character associated to this module? And this is where things become more manageable, because to determine the character, we do the following. We take G in G and consider the action of this G on the right on this module. Okay? So we had seen that this module is a direct sum of this stuff. So let's look at the matrix. So let us look at the matrix, which is then rho of G at the matrix, rho of G of this action. In the basis, with respect to the basis, to the natural basis, which is given by this direct sum. Okay, which means that here we have WT1, which is then W times 1. That times, okay. Okay, and the same here. And so this is a block matrix. Okay, and since we are interested in the character, we just need to look at what happens on the diagonal, right? Because the character will be the sum of the elements on the diagonal. Okay, so we take one of the T. So let T be an element of T. Remember, T is this script T is this transversal. The elements are T1, Tk. But if I want to take an arbitrary element, I simply call it T. And we wonder, so let W be an element of W, and we wonder what happens when we apply G, okay, on this. Well, so the idea of this bimodule stuff is that this is a CG module, okay, this, okay. How? Well, it's the action by multiplication on the right here, okay. So this will be simply, well, let's revert to black. TG, okay? But written in this form, this does not fit in this decomposition, okay? Because we know that any element of this, in particular the element I've just written, must be here. So how do you write it in one of this form? Well, the point is that TG is an element of G, so it belongs to one of the cosets HT1, HTK. So this means that TG, okay, will be of the form HT prime. Okay, so this TG, and it's an element of G, so it's an element of one of these cosets. Suppose it's the element of the coset HT prime, okay? And then, so for some T prime in T and H in H, okay? Then let's continue from here. W times TG is W times H T prime. And now this H, okay, look here. Since this is a tensor product over CH, this H on the left here can go on the right here. That's the point of tensor product, that you can move from left to right the elements of this, okay? So this will be WH tensor T prime, which is now in one of these subspaces, okay? But the point is, if T prime is different from T, okay, what happens is that this is not on a block on the diagonal, okay? So this will contribute to a character only if T prime equals T, okay? Because then you are in a block diagonal. So suppose, for instance, that multiplying by G, W tensor T1 goes to W tensor T2. I mean, it's something here, we have something here, but we don't have anything on the diagonal. So that there's nothing to contribute to the character, which is the sum of the elements on the diagonal. Okay, so in this case, and in this case, okay, and in this case we have that H will be, this is the case when T prime equals T, it is TG T inverse, okay? Or in other words, G equal T inverse HT is in the conjugate of H through T. So what happens here? There is a contribution on the diagonal, okay? So this becomes like this, where the character is the character of this element H, okay? Because here on this block, say, for instance, we have that what happens, you started with W tensor T and multiplying by G means simply multiplying by this element H, okay? So the character would be on this block, would be the character of the element H. But this happens only when G is in one of the conjugates of H. Okay? Good. And with this in place, we are ready to give the definition of the induced character, or in the induced class function. So the idea is the following. As usual, you have H subgroup of G. Then you have a function. Let me check which notation I want to use. Well, okay, let chi from H to C be a function. It does not need to be a character or a class function on H. It doesn't matter. We'll get a class function on G anyway. So, and then first of all, you define the chi naught from G to C, okay, which is simply the following. Chi G is chi of G, chi naught of G, if G is in H. Otherwise, it's 0. So you have simply extended chi from H to G by declaring that outside G, okay, if G, that is G is not in H, then outside H, sorry, the value is 0, okay? And then you define the induced function on G as 1 over the order of H. This is for technical reasons. And then you sum, no, sorry, I made a mistake. It's better to use the letter X here. So the sum G in G of chi naught X of G. Okay, so the notation is slightly different from what we saw here, but yeah, unfortunately, but anyway. So note. Okay, a couple of notes. First of all, note that no matter what kind of function chi was, so 1, chi G is a class function on G. Meaning that that is constant on the conjugacy classes, and this is easy to see because if you consider the value on a conjugate, okay, so this is this factor will become clear later. So x, y, g, okay, because x, y, but this is of course x, y, g, because I mean conjugacy is in action, and of course y is fixed. But if you but when g ranges over g, these products also range over g. So if you change the variable, and we call it g prime in g, we will get exactly the same. Okay, so we have set g prime equals yg. So y is fixed, and as g ranges over, and then the multiplication by y is a bijection. Okay, so you see that this is exactly the same value the same value of x, because we are summing. This is a dummy variable. It doesn't matter the name of this variable. Okay, so this is the class function. Moreover, as we were seeing in the previous calculation, moreover, chi g of x is different from 0 if and only if x is in h t for some t. And the reason is quite simple, because this for this to be different from 0, there might be a g. Okay. Okay. Let's copy this and get to the next. Okay. For this to be non-zero, for chi gx to be different from 0, we need that one of these summand is different from 0, and so we need there is a g in g such that xg is in h. Okay, because chi naught is defined as chi g if g is in h, but otherwise it's 0. So if all this conjugate, if none of this conjugate is in h, this will be a sum of zeros. And of course, xg is in h means is the same thing as saying that x is in the conjugate of h through g inverse. So this is a function which is 0 outside the union. So chi g is 0 outside the union, let's say for g in g of h to the g. Okay. So it can only be different from 0 on the union on the conjugates of h. And that's, let me see, just a second. And that's point 2, okay, point 2. Okay. Fine. So the reason why we chose this is exactly given by this argument, because when we want to see the character associated to this module, the only way of having a non-zero contribution is when G is in a conjugate of H, and then the contribution will be this element of the contribution given by this element H, which is the conjugate of G. Okay, and so hence you see the conjugate of X in this case, because I've changed variables, unfortunately. Okay, good. Now, what I want to prove, we want to prove, claim if chi is a character of H, then chi G is a character of G. And to prove this, we prove a very important formula, which is called the Frobenius Reciprocity Theorem. Oh yes, I have too many. Just a second. Okay, so this is the formula that I wanted to. Okay, let me copy it to the previous, because it belongs really to library. And then we go here. We let's see. We move this a bit down. And wait just a second. Pictures. This is the one, and I'll put it here. No, here. Okay. So this is what I the claim 2. It's really this one. No, sorry, just a second. Undo. That's so the claim 2 is really this, okay, or which is equivalent to this. Okay, so we can erase this because we have moved it to the previous page. And now this important result, Frobenius reciprocity theorem. Which explains why in this formula we have a divided by the order of h. And the claim is the following. Let theta be a class function. As usual, we have h a subgroup of g, and g is a finite group. A class function on g, and phi a class function on h. So we can do the following. If we have a class function on g, then we can consider the restriction theta h, which is a class function on h. And if phi is a class function on h, actually, I mean, meaning that these are functions, theta is a function from g to the complex number, and phi is a function from h to the complex numbers, particular characters, and then phi to the g, the induced class function, is a class function on g. So we have 4 class functions, and we can consider the two inner product. One is theta phi to the g, because this is the inner product on g, and we can consider also theta h, which is a class function on h, phi, the class function on h. Okay, and what the theorem tells you is that these two are equal, and we see why this is important, because it will prove in particular that if you start with a character on h, then the induced class function on g will be a character. The proof is not too difficult. Let's see if it fits here. Yes, it should fit. So we start with this. Okay. So what's this? It's the standard inner product where we sum over x in g. Remember that we have to take the conjugate here, and then we have phi of g of x. This is the induced function. So this is another sum. Which sum? It's this sum here. So you divide by the order of h, and then you sum over g in g, this chi naught of the conjugate. Okay? So it means that we will have 1 over g, then 1 over h, because this is this 1 over h here. Okay? And then we are summing over x and say g, theta x, phi naught of x to the g. This is what this formula here says. Okay, you sum over g, and then you take phi naught, in this case chi, but phi naught of the conjugate. Okay, good, and this is just the conjugate. But of course we can make a change of variable, and the change of variable is we set y equals x to the g, which of course means that that x is y g inverse. Okay, it's just a change of variable, and since conjugation is a bijection, you can do this change of variables. And okay, so this will be 1 over g, 1 over the order of h, sum y g in g, and you have the theta of x will be y g inverse, and this would be simply phi naught of y. Okay, the change of variable, since conjugating is a bijection, summing over x or over y is absolutely the same. But know that theta, by definition, is a class function. Okay, which means that all these values, when y is fixed, all these values are the same because are just value over conjugate. Okay, so when you sum over g, there's no g anymore here. All these elements are equal, and there are, of course, order of g of them. Okay, so this means that we obtain 1 over. Okay, let's do it properly. 1 over order of G, 1 over order of H. Order of G times, the sum over G has disappeared. Okay? Because all the elements, I mean, once you fix Y and you let G range in G, then all these elements are the same. So you get order of G elements, which are all equal. And so these two G cancel out. But remember that phi naught is simply defined as phi on H and 0 otherwise. So you have a sum over G, but the sum is 0 over H, because when Y, remember that phi naught of Y is 0 if Y is not in H. Okay? So this means that what you have obtained is the sum for Y in H of theta of Y, and now simply phi of Y. Okay? Because the values, when Y is not in H, this is 0, so there's no contribution. And you see that this is exactly this inner product. That's the reason why we had this thing here, so that it's an equality that there is no factor, and this is simply theta H and phi. Why theta restricted to H? Because I mean, simply because restriction means simply as a function on H, and of course here we are evaluating theta only on elements of H. Okay, so you see there is this kind of duality between the two operations of restriction. Simply you have a function and you restrict it to a subset on G, and you restrict it to a subset H, and this operation of induction. Okay, and the proof, if you go through it, is really not very difficult. I mean, even if the tensor product stuff looks a bit complicated, you can safely start from this formula, and this is elementary enough. I mean, you don't need too many complications. But then why does this formula show what I claimed earlier? So first of all, let's copy this formula to the next board. Okay. And this formula, from this theorem of Frobenius, you obtain a corollary which says that if phi is a character of H, the situation is as usual that H is a subgroup of G. If phi is a character of H, then phi G is a character of G. Why do we have to prove this? Because so far, we only know that phi to the G is a class function, okay? So far. We only know, it's point 1 that I proved earlier, we only know that phi G is a class function from G to C, okay? It's constant on classes. That's what it means to be a class function. Well, we know, we have proved at the beginning of the course, after the orthogonality relations, that characters, irreducible characters, are a basis of the space of class functions. So phi of G is a linear combination with possibly, say, with complex coefficients of the elements of the irreducible character of G. Recall why? Because I mean, the dimension of the class functions are a vector space over C. I mean, you simply, as all the maps to C are, and then their dimension is the number of conjugacy classes. Okay, because class function means that it takes one value for each conjugacy class. And we know that the number of conjugacy classes is the same as the number of reducible characters. The reducible characters are orthogonal with respect to the inner product, and so they form exactly a basis of this space of cross function. So this phi g is a sum of irreducible characters, but these elements so far are elements of C. Okay. What we want to prove? We want to prove that need to prove ik is a non-negative integer. Because if it's a non-negative integer, then phi g will be the character of representation. Okay? Why? Because so that chi is the character of the representation. Let's write this explicitly. Okay, that's so let's write v chi1, more explanation in a second. A chi1, v chi2. So let me write and then I'll explain what this is. Okay, where say v chi I is the CG module corresponding to the character chi I. Okay, so if these are non-negative integers, okay, then you consider this representation. If you want rho I from G to GL via v chi I is the representation affording the character chi I. Okay, so you write this representation, and what's its character? Well, it's a chi1 plus a chi2 and so on, and so it's exactly the character of this representation. It's exactly this character. So if these are non-negative integers, otherwise how can you say that, I mean, if this is, for instance, negative or a complex number, there's no meaning in taking a chi1 copies and taking a direct sum of a chi1 copies, okay? So you need to prove that these are non-negative integers, and then phi g will be the character of this representation. How do you prove this? Well, the point is that a chi. Okay, no, I need to copy this to the next slide. Well, which means okay. So let me take this. Yes. Okay. So we need to prove that a chi, to be proved, a chi is a non-negative integer. How do you prove this? Well, a chi, by definition, is the scalar product of phi g with chi, okay? The inner product, okay? Because the chi, the reducible characters, are orthonormal, okay? So if you take the inner product of phi g with a certain chi, you isolate a chi. But by Frobenius reciprocity, this will be the same as phi chi h, as the inner product, where, remember, phi, let's see the hypothesis, phi is a character of h, okay? Phi is a character of h, and this is a character, okay? Just a second. Yes. And so this is the scalar the inner product of two characters of h. And so this is a non-negative integer. Why? Well, because because okay, fine, let's write it, because these are two characters of H. Okay, so both of them can be written as let's use a different letter. Okay, sigma in the irreducible character of H with B sigma sigma, and chi H equal sum, let's say tau in the reducible character of H, C tau. Okay, so I mean they are two characters of H, so they are a sum of characters, irreducible characters of H, with B sigma and C tau, which are non-negative integers. Okay. And then what's this product? Well, because the sigma, these are orthonormal, this will be simply be the sum for sigma in H, B sigma, C sigma. Okay, because these are orthonormal as usual. I mean, irreducible characters are orthonormal, meaning that the only way to, I mean, if you take two different ones, the inner product is 0. Okay, whereas when you take the same, the inner product is 1. Okay, and this, of course, since these are non-negative integers, this will be a non-negative integer. And so we found that the AK are non-negative integers, and this proves that the induced character, this is indeed the character. Okay. We see an application of induced characters in the last 3 hours. So in 2 weeks' time. Remember, there are no lectures next week. To an important theorem again of Frobenius, I mean, one could see that induced characters are also useful for constructing characters of a group, starting from characters of a subgroup. But I don't want to go into many details, though it would follow from this stuff, because I want to dedicate the rest of the lecture to one of the two main applications of our theory, and the application is a theorem of Burnside, which I have announced several times during the Burnside PAQB theorem. Which says that a finite group of order divisible by at most 2 primes is soluble. Okay. Yes, we discussed soluble groups at the beginning of the course. I will remind you of the features I need of soluble groups. And so why PAQB? Because, of course, if it's divisible by at most 2 primes, and the 2 primes, the order, these 2 primes are P and B, then it means that the order of the group is something like P to some A and Q to some B. Okay? And of course, example, we know that A5 is non-abelian simple, non-abelian and simple, because recall that the only simple soluble groups are prime order. So this is not abelian simple, and the order of A5 is 60, which is 2 squared times 3 times 5. So 3 primes divide the order of A5, as it should be, okay, because of Frobenius theorems, of Burnside theorem. I understand, I know very little of the history of mathematics, but apparently in the beginning Burnside did not believe too much in the theory of the theory of characters developed by Frobenius, and then he realized how powerful they were, and proved this theorem using characters. And the precise dates are in the notes, but it took several decades to group theorists to find a proof of this theorem which does not require characters. With characters is relatively easy, whereas it took decades to many valiant group theorists to find a character-free proof. Okay, so let's approach this proof. This proof will require some discussion of algebraic integers. So let's start with this lemma, okay, which says the following: let G be a group, let chi be a character. Let me see whether I'm only requiring it to be a character or I want to be more than that. No, simply a character of G. And G be an element of G. Then the first statement is that this element, so the order of the conjugacy class of G times chi G divided by chi1 is an algebraic integer. Note that, of course, the order of the conjugacy class of G is a positive integer, so it's an algebraic integer, and chi G is an algebraic integer because it's the sum of roots of unity. But since you are divided by an integer, you are not sure. I mean, you know that the only rational numbers which are algebraic integers are the integers themselves. So the fact that there is a denominator here requires a proof, okay? And then there are two more things which are valid if furthermore a certain condition holds. The condition is actually, as you will see, natural in the context of Burnside PAQB theorem. And the condition is that the order of the class and the degree of the character are coprime, okay? And then we have two more statements. First of all, that this quotient is an algebraic integer. And then the third one is that if chi of G is different from 0, then rho of G is scalar, where rho is a representation affording chi. So I mean, if chi is a character, it means it's a trace of a certain representation. Call rho any representation which has character chi. Okay, we see that all these come rather naturally. In fact, point one we have in practice already seen, but it's useful to remind us of certain things that we have seen a few weeks ago. So let's start with this. So remember that we have proved earlier. that if you consider, okay, recall that the center of the group algebra, okay, as a basis, the sums of conjugacy classes, okay, for G and G. Remember that this means that you take the distinct elements of the conjugacy classes and you take their sum, okay, as a, say, C basis. And so this is the center. And then we had considered we know that the set of Z linear combinations of these sums is a ring, because we have proved that the product of these two classes is a linear combination which integers coefficients of other classes, and since it's a finitely generated as an abelian group, finitely generated by what? By the finite classes, because it's is the set of linear combination of these sums of the conjugacy classes. And of course, since G is finite, the number of conjugate classes is also finite. Since it is finitely generated as a Abelian group, remember we have proved, not in all details, then this ring, let's call it R, then R is integral. Okay, all of its elements are integral. Meaning that they are roots of a monic polynomial with integer coefficients. Okay? In particular, the sum, in particular, this is integral for a fixed or an arbitrary G in G. So if you take the sum of the elements of a certain conjugacy class, this will be an integral element. So it will be a root of a monic polynomial with integer coefficients. And now we take the usual isomorphism. Okay, remember that we have an isomorphism between the group algebra and let's say the sum over the irreducible characters of matrix rings of dimension chi1 over C. Okay, this is a standard isomorphism that we have discussed several times, and we consider the composition with the projection over one of these for a particular chi. Okay, for the chi we are discussing. For the chi, let me see just a second. Okay, then I have to add something here in the reducible character. Okay, so it's an irreducible character I'm going to consider, because if I want to take this projection, I need the irreducible character here. Okay, so we have this morphism. This is an isomorphism, and the composition is a morphism. And so, in particular, we can take this element here, and this will go to what? Since this is in the center of the group algebra, this is a discussion we have done several times. This will go to the center of this, which will be a scalar matrix. And after all, what does this map do? It simply takes an element G and then takes it to rho of G. Okay, so this means that in this function, sum G under this function goes into what? Goes into the sum for yes. Okay, so suppose that this conjugacy class is given by this element. Okay, and this class has exactly n elements, and then this will go in the sum. Okay, let's write it explicitly. Rho of gx1 plus rho of gxn. Okay, and remember this is a scalar matrix. And as usual, how we compute lambda, we have done this at least a couple of times. We compute lambda by taking the trace. Okay, so on the right, we will get lambda chi1. Okay, because remember this is in a matrix ring of dimension chi1. Okay. On the other side, you will have the trace of this. Okay. Of course, the trace is linear, and the trace of rho is the character. And the character is a class function. So all these elements are equal. So what we get n is the order of the class, we get order of the class times chi of g. Okay? So we find that this lambda on the diagonal, this is the argument we have probably already seen, is exactly this. Okay, because we have divided by chi of 1. This, I write this down, but let me first state it in words. This is integral. It means is a root of a monic polynomial with integer coefficients. But then, of course, when you apply a morphism, this is also integral. So this matrix is the root of a polynomial, an integer polynomial, monic polynomial with integer coefficients. But then it means lambda is an algebraic integer. Okay, so if sigma is a root of a polynomial, of a monic polynomial, say f with coefficient in z, but remember monic, which means integral, then since we have a morphism and a morphism sends integers to integers, then this matrix is also 0. Okay, so this is a root of a monic polynomial. So 0 is the sum f of this sum, but then you apply this morphism. This is also a root of f, and of course, how do you compute a polynomial on a scalar matrix? This is just the matrix f lambda. Okay, this is the 0 matrix, so f lambda is 0. Meaning lambda is an algebraic integer. Okay, so from the fact that this is a integral, remember the term as an algebraic integer is reserved for elements of the complex numbers. In general, if you have a commutative ring of characteristics 0 that is contained in the integer, you say that an element is integral if it's a root of a monic polynomial with integer coefficients. I mean, this polynomial, this element here is a root of f, and then this lambda is a root of f, and then lambda is an algebraic integer. And of course, lambda is exactly this element here, as stated in the theorem, okay, in the lemma. This is an algebraic integer. Now we want to prove that if these two are coprime, then first of all, chi of g over chi1 is an algebraic integer, and this is easy enough because okay, we have proved that lambda is an algebraic integer. Okay, well, no, I don't need to copy this, so I'll simply write. We know that this is an algebraic integer. And remember, this is not obvious because we are divided by an integer. Now, if the greatest common divisor between this and chi1 is 1, well, you should have a conditional reflex and think of Bezout's theorem. There are integers such that a plus b chi1 equal 1 actually is an if and only if. And then since I want this to pop up, I multiply by chi of g divided by chi of 1. And what I obtain here, well, first exactly the element I wanted. Okay, and here when you multiply this, well, chi1 simplifies, you get chi of g. Okay, and here you get chi of g divided by chi of 1. Now you know that this is an algebraic integer. And this is even an integer, this is an integer, and this is an algebraic integer. Okay, so let's simply point to the same statement. I mean, we knew from the start that the value of a character, I mean, it is a sum of roots of unity. Well, this is important, so let's recall it. Recall that one of the first arguments we had in representation theory is that if you have a representation ρ, you apply to an element G of order n, and then you find that ρ of G can be put in diagonal form with nth roots of unity on the diagonal, and so the character is the sum of nth roots of unity, and then it's the sum of algebraic integers, and then it's an algebraic integer. Well, anyway, on the left here, we have several algebraic integers, and we have proved that the algebraic integers form a subring of the complex number. So it follows that this is an algebraic integer. As algebraic integers, as the algebraic integers form a subring of the complex numbers. Not a subfield, because I mean, if you divide 1 by 2, you get 1/2, which is not an algebraic integer, but a subring. Okay, so this is what we, the statement 2 in the lemma, that if if these two are coprime, then this is an algebraic integer. And then we have are left with proving that if the value of the character is different from 0, then ρ G is scalar. Okay, and why is it so? Because you see, it's the argument I was discussing just a second ago. Okay, so we know that chi of G over chi1 is an algebraic integer. And let's write down what the argument I just explained in words. So suppose that ρ affords chi. Okay, so ρ of G can be put in diagonal form. Okay, meaning choosing a suitable basis with element omega 1, omega whatever, omega k on the diagonal. Okay, I mean, ρ of G is not necessarily of this form, but you can find a basis so that that is of this form, 0 of the diagonal, where omega I are nth roots of unity. Okay, and where n is the order of G. Okay, just think for a second. Yes, fine. And oh yes, with this k is just chi of 1, and so this means that this chi of G over chi1 is exactly, well, okay, it's omega 1 plus omega k divided by k. And there is a lemma that we proved some time ago. It's not terribly difficult, but it's lemma 1.11.13 in the notes. Okay, I mean, in case you need to see it, is that if you have an element which is a sum of roots of unity, many roots of unity, k roots of unity divided by k, if this is an algebraic integer, okay, then there are two possibilities. Either chi of G is 0, I mean, this is 0, but in the lemma, we explicitly rule this out. Chi G is different from 0, okay? So this is ruled out. Or the alternative is that all these are equal, but then this means exactly what we wanted. Let's say that they are equal to some omega, that the ρ of G is a scalar matrix. So we use this lemma that tells you that if you have a sum of k, well, in the formulation of the lemma, it was n, but I mean, of course, it's any number goes. So if you have the sum of k roots of unity divided by k, and this is an algebraic integer, so one possibility is that this is 0, like 1 plus minus 1 divided by 2. Okay, this is possible. But if it's not 0, then all these are the same. This means that rho of G in this case is a scalar matrix, so a matrix, a diagonal matrix with the same value on the diagonal. Well, having proved this, we are ready to prove Burnside theorem, and we'll do it through another lemma, which may look technical, but it's exactly what will happen in the group we'll be dealing with. So we have G, a finite group. Well, this comes as no surprise by this stage. And then you have an element of G, which is different from 1, such that the order of the conjugacy class of G is a power of, well, let's say, p to the c for some prime c, and of course some c which will be, of course, greater than 0, because if c is 0, then the order of the class is 1. C, well, it doesn't, the same greater than 0, yes. Okay. Then our claim is there is then there is a normal subgroup of G. Well, okay, let's put it clearly. Okay, I'll write it in words. Then there is a proper normal subgroup of G, normal subgroup N of G. So proper means that N is different from G, and normal means normal, but it's not G, okay, of G, such that Gn is an element of course, of the quotient group, G over N, and it's normal, but it's actually in the center, okay? So let's see how you prove this. Note that there is no trace, well, okay, sorry, this was an unintended pun. There is no trace of characters here. In no place here we see characters named, but we will see in a second that they enter in the proof. So let's see the proof. Well, since G is different from 1, okay, in particular, G is not conjugate to 1. Because the only conjugate to 1 is 1. Then the second or the other, then the second or other orthogonality relation yield. So the first orthogonality relations tell you something when you sum over G. The other, which are simply a matter of exchanging a product of two matrices, tells you that the sum over all irreducible characters of G, of chi1, chi-G, is 0. Okay? Because, because the product of those two matrices is a diagonal matrix, and this is an element of the diagonal. This is because G is not conjugate to 1. Okay? But if this is, just a second. Yes. Of course, one of these summands here is when chi is the trivial character. Okay? So we can rewrite this as a sum. Okay, chi is irreducible, but let's the sum when chi is different from 1, and 1 is the trivial character. Okay, 1 of G of X is 1 for all X in G. Okay, and so this will be equal to -1, because I mean, if you take the trivial character, you will have 1 times 1. Okay, so I simply take the sum over all characters except the trivial one, which is the character which we always have in the first line of the character table and which has all values equal to 1. Then divide by p, okay? Okay, and so we get sum chi different from 1. Let's say chi 1, yes, chi g divided by p equals minus 1 over p. Now the point is, this is a prime, okay? So this is not an algebraic integer. Because it's a rational number, and the only rational numbers which are algebraic integers are the integers, okay? And this, of course, is not an integer. I mean, it's so this means that not all terms here are algebraic integers. I think I will have to copy this to the right. So let me rewrite this before copying. So this is not an algebraic integer. Let's copy this to the next. Yes. So we know that this is not an algebraic integer. So this means then there is a chi, which is a irreducible character, which is different from 1, from the trivial character, such that this is not an algebraic integer. But then if this is not an algebraic integer, but then this means that P does not divide chi 1. Remember, chi 1 is an integer, is the size of a matrix. If P divides chi 1, because otherwise, because the reason is trivial, but let's write it. If P divides chi 1, then this can be written as this, which is an integer, times chi g, which is an algebraic integer. And so this is an algebraic integer. Okay, so if P divides chi 1, this is an integer. It's an apparent fraction, as we say. This is an algebraic integer. We have repeated this several times. So this will be an algebraic integer. Since the sum is not an algebraic integer, one of these is not an algebraic integer. And this will mean that for that particular chi, P does not divide chi 1. Okay? But if P does not divide chi 1, okay, then the greatest common divisor between the order of the class of G and chi 1 is 1, because we had assumed that this is of the form P to the C, okay? And since the only non-trivial divisor of P to the C are powers of P, and P does not divide chi 1, this might be coprime. I mean, the only possibility would be to have a factor P in common, but P don't divide, that does not divide this. But remember, we had this lemma. We said that in this case, then if rho is the representation affording chi, then rho of G is a scalar matrix. Okay? Just a second. Yes. Just okay, fine. Rho of G is a scalar matrix. So we have this representation G in GL V. Okay, it's a representation associated to this character chi, and by the usual isomorphism theorem, we have that G over the kernel of rho is isomorphic to rho of G, which will be a subgroup of GLV. Okay? Just a second. Yes, okay. But note, yes, this is important. Rho G is a scalar matrix, but rho G is different from 1. Different from 1 because otherwise chi G is chi 1. Okay? Because I mean, if this is I mean, otherwise, if rho G is the matrix 1, then chi of G is chi 1, and this means that that this is an algebraic integer. No, wait a second. Just a second. No, well, just a second. I'm missing a point. No, this is not what I wanted to say. Sorry, this is a different thing. Let's erase this. Okay, moreover, okay, so we have this. Moreover, let's call N equal kernel rho is different from G, because the only reducible representation that has kernel G is the trivial one, because chi is different from 1. Okay, so the only reducible representation. Rho with ker rho equal G is the trivial one, the one with character 1. Because if you have any other character, it will have a value different from 1, which means that this element is not in the kernel. Well, okay. Good, yes. Well, it's slightly more complicated let me see whether I should explain. Well, I'll be back to this in a second. Okay, since chi is different from 1, the kernel is not G, and we have this isomorphism, okay, which I will copy again. I mean, this is the day of copying things from one to the next. Except that I want to, no, okay. Just a second, let me see how I organize things, because I copied, no, I didn't want to do this. Well, let's forget about this. I'll erase that board. So remember, we have that rho of G is okay, that G over the kernel of rho is isomorphic to rho of G, which is subgroup of GLV. Okay. So what's the claim I have? The claim is that there is a proper normal subgroup such that this coset is in the center. Okay. But note that rho of G of this element is a scalar matrix. So it is in the kernel, it is in the center of GLV even, and in particular of G. But this is an isomorphism, okay? Since G over kernel of rho is an isomorphic, so if rho of G is in the center of this, then this means that the element corresponding here, and the element here is G ker rho, okay? This is in the center of this. Okay, because in an isomorphism, the center goes to the center, and this is exactly what I wanted to prove. Okay, because what I wanted to prove is that this element, there is a proper normal subgroup. This is the kernel. That this is in the center of this. Let me just a second. Oh, well, it's a bit of a mess here. I'll have to rearrange this later, the boards later, because I went back and forth. I want just to clarify this. Let me clarify this. So the only reducible representation rho with kernel equal G is the trivial one. And the reason is that if, let me see if I have time to finish. Yes. If rho is an irreducible representation, with kernel rho equal G, okay, then its character, then I mean, if you have rho of G equal the matrix 1, 1, 1 for all G, okay, then the associated character is, well, chi, if this is a matrix of dimension n, is chi of G equals n for each G, okay? Because the trace of this is n. But this is 1 plus 1 plus 1 n times, and this is simply the value of the character 1, okay? Trivial character. But if this is irreducible, okay, it cannot be the sum of irreducible characters, except when it is 1, okay? Because the sum of characters means this is isomorphic to the direct sum of certain representations, but if it's irreducible, it has to be only 1. And so you see that chi G is 1 for all 1, okay, for all G. Good. Let's finish and then I'll rearrange the boards. We are ready to give the final proof of Burnside theorem. And there are two cases. The first case is G is a P group. There is G as order P to the A, so there's only one prime for some prime P, and A, which I'll take a greater than or equal to 1. Okay, so let's say G is different from 1, because if G is 1, of course, it's trivial, that is soluble. And then you recall from the Teoria di Gruppi course that if G is a non-trivial P group, then the center of G is non-trivial, okay? And this is abelian, hence soluble. Okay, and by induction on the order of G, G over ZG is soluble. Of course, you start with a group of order P, which is abelian, and recall that if you have the soluble groups have the property that if a normal subgroup is soluble and the quotient is soluble, then G is soluble. Actually, G, a P group is more than soluble, is nilpotent, but one of you will be given a seminar on nilpotent groups, and so this will be a chance to see also that. Let's see what happens when the order of G is PA QB, where P and Q are distinct primes, and both A and B are greater than 0, then you see, okay, fine. First of all, we have to recall things that we discussed at the beginning of the course. You take a composition series of G, And so the composition, if you take a composition of series of G, the composition factors are simple. This is something we proved at the beginning of the course. If they are all abelian, okay, and then of a prime order, then G is soluble. We recall that soluble means one of the equivalent statements is that it has a composition series with abelian factors, okay? So proceeding by way of contradiction, assume one of the factors of the composition series is non-abelian simple. And call it G for simplicity, okay? So we have reduced to the case when G, of course, all factors have also order P to the A, Q to the B, I mean, and we have reduced to the case when they are non-abelian simple, okay? So simple but non-abelian, so not of prime order, okay? If one is the only conjugacy class of order not divisible by Q, one of the two primes. So suppose that all conjugacy classes have order divisible by Q except for the class of 1. But then since the conjugacy classes are a partition of G, you will have that the order of G is congruent to 1 mod Q. Because you have all the conjugacy classes have order divisible by Q except this class, okay? And this, of course, doesn't fit with the fact that G is order divisible by Q, okay? So Q does not divide the order of G, contradiction, okay? So it means that 1 is not the only conjugacy classes of order not divisible by Q. No. So let G be a class of order P to the C with a G different from 1. And so, yes, yes, of course. So suppose that this class is not as order not divisible by Q, then it has order divisible by P, okay? With G different from 1, and C has to be greater than 0, because otherwise you have an element in the center, which is non-trivial. And okay, is that clear? I mean, there has to be a class whose order is not divisible by Q, the class of one order element independent from 1. And so the order of the class, which is the divisor of the order of the group, can only be a power of P, because there is no Q in it. But then you see, since G is not abelian simple, we have two facts. If N is a normal subgroup of G, N different from 1, then N is 1. Okay, because non-abelian simple means that the only, the only normal subgroups, different from G is 1. Okay? And moreover, the center of G has to be 1, because the center is a normal subgroup. It cannot be G, because G is non-abelian, and then it has to be 1. But then the lemma we just proved, tells us that by the lemma, G let's write it is in the center of G, which is only one, a contradiction. Okay, because G was different from 1. Why is it so? Because the idea is that Gn is in the center of G over n for the lemma said for some subgroup n of G different from G, but the only such subgroup is 1. Okay, so I mean, this is 1, and so we get this. G is in the center. And this contradiction proves Burnside theorem. Okay? So as you see, the proof is really containing the previous lemmas. Okay, which and in particular in this lemma that tells you that oh, well, this is messed up. Yeah, if you have an element in a finite group different from 1 whose class has order power of a prime, then in a certain quotient is in the center. So if you reduce to the case of non-abelian simple, we get the result. And you saw how we were able to find such an element in a group in a group of order PAQB simply by noting that one could not possibly be the only conjugacy class of order not divisible by Q. Good. So that's all for today. No lectures next week, and see you in a couple of weeks' time for the final result on Frobenius group. We will. Okay. Fine. Thank you. Bye.